go with the presentation first, and please keep your questions for the last 10 minutes of the seminar. Please go ahead.
Thank you, Mani. Thank you, everyone, for attending this seminar. So like Mani said, my name is Zhao Wang, Associate Professor from Iowa State University. So it's my great honor to be here because WSU has a very prestigious top power program nationwide, even worldwide. So I'm very happy to be here and enjoy the visit a lot till today. And my presentation title is leveraging data to enhance power distribution system grid modeling and operation. So my research purely focuses on power distribution systems. Anything below 35 kV belongs to the distribution system in North America. So that's my research area. So we do data, we do optimization, but today certainly we can't cover everything. So this focuses more on data. And this is just a figure showing you the power system, very simple figure from the generation to the transmission to the distribution side. And I'm focusing on this green distribution side that's closer to the customers, your houses. And where the data coming from at the distribution side? At the distribution side does not have any data in the past. That's the truth. And even for now, many utilities don't have too much sensors or observability at the distribution side. But when we talk about smart grid in distribution, grid modernization, we're talking about a few sensors at distribution grid. One is smart meters. You probably heard about that can measure the reactive power, active power, mostly active power, and the voltage every 15 minutes or every hour, and send you the energy bill every month. So that's smart meters. And another one is micro PMU. There's pretty advanced and very fast sensors that can sampling 120 samples per second. That's micro PMU. They even come with a P-cube sensor that's even faster, can do the point on the wave measurements. But they're rare, very rare because of the expense. And also the SCADA has been there for quite a while, but SCADA, most utilities only measure the feeder head at the substation level, so not down to the remaining part of the feeder, mainly just measure this part, and measure the PQ and V, or voltage and current, and at different resolutions. Sometimes as fast as full samples per second, sometimes go very slow, like a few samples, just a few minutes. So depending on utility settings. So at least a few utility companies' names. Some are ComEd in Chicago, Atlanta Energy is in Iowa, is the largest distribution company in Iowa, and some other utility companies in Iowa we're working with, at least them, because all the data are real data coming from these partners. So we rely on them to supply data to us to do research. For example, for ComEd, later on you will see we use their SCADA data to do the CVR analysis. That's what I will present. For Atlanta Energy, this micro PMU, I want to mention that's the very first micro PMU project in the whole state of Iowa. So Iowa State has a great honor to lead. Actually, I lead that project and install 7 micro PMUs at Atlanta Energy to monitor the renewable energy and their impact on distribution systems. So that's the very first one in the whole state of Iowa. I think ComEd is a little ahead of us. Other than them, we are almost the first in the Midwest region to do that. And the smart meter, we use the data for many applications for the load profile analysis, for the system modeling, for distribution transformer overloading analysis, all this kind of analysis for the distribution utilities. So today, certainly I won't be able to cover everything. So what I will focus on is 2 topics. One is the conservation voltage reduction. We use SCADA data to analyze its energy saving effect. So that's basically our idea is to identify the load to voltage sensitivity. Basically, you have voltage change, what's the load change? So that's load to voltage sensitivity identified from SCADA data at the feeder head level. And the other one is voltage estimation in the secondary distribution systems. That's using smart meter data. That's opposite, identify the voltage to net load sensitivity or voltage to the nodal injection sensitivity. Basically, you have different nodal injection sections, you want to identify what's the voltage, okay? So different sensitivities identified using different types of data, smart meter and the SCADA. So that's what we are going to talk about today. Let's talk about CVR firstly. What's CVR? It's a kind of energy efficiency measure that reduces the energy consumption by reducing the feeder level voltage. So it's pretty simple. Basically, utility just reduce the voltage at the feeder head using their voltage LTC, low tap changer, that reduce the voltage a little bit, but still within the ANSI. You probably heard about ANSI. Still within the ANSI standard. It's just a lower range of the ANSI standards. So won't affect anything, but you reduce the voltage. And the major benefit is that it's kind of non-intrusive because customers don't even know what's going on, and it's happened automatically. It's not like the demand response. You have to control customer, right? So this is you don't have to control them, and they don't have any just a problem or any feeling about this matter. And this CVR, you can see that how it works. You reduce the voltage a little bit, and usually a few percentage. It's expecting that your energy consumption will be reduced. Okay, so this red dotted line is what if I didn't reduce voltage. Of course, I don't know what if I didn't reduce voltage. But if I know that the difference between the two, that's a green side, green area, that's an energy reduction due to the CVR, right? That makes sense. So an important thing we need to consider is the CVR factor. So that's by how much voltage you reduce how much energy. So this is a simple definition metric to just show you the effectiveness or the performance of your voltage reduction. So why this CVR factor matters? Why it matters? Certainly utility wants to know how much energy I want to save, right? So, but that's not the only reason. The most important reason is that most regulation agencies, every state has a utility board or utility regulation agencies. They require utilities to report this number every year. You must report that because you claim you save this energy. But whether it's true or not, I don't know. You must report that. So that's why it matters. So this is a very industry-oriented work. So we are working with ComEd on this IEEE standard pre-3102. If you're familiar ever with the IEEE standard, you know it's a long process. This standard has been going on for 4 years. So we're still in the revision process, hopefully to finalize that in a few months, become an official standard. You do this through IEEE technical committee. For our case, it's a TND committee. You do that through IEEE Standard Association. That's a separate entity, the IEEE. So you get approval from them. They have a ballot, and our first ballot has already approved with a 96% approval rate, so we're okay. So after submit revision, there's a second ballot, usually is done. Then it become an official standard. And this standard has multiple sections, including data collection, data cleaning, data reconstruction, and the methodology selection. So methodology selection is to tell you which methodology you should use to evaluate the CVR factor. So that's the key, right? So eventually you want to know which methodology I need to use. And the previous three sections just help you to collect the data, clean up the data for the last section. So I'm the lead of the last section, and so I will present part of the work there in today's presentation. What kind of methodology we will use to evaluate the CVR effect? Well, actually, there are many simple methods used by industry. First method we call the comparison method. Okay, I define it as a comparison method. Look at this figure. So if you have one feeder, you do the voltage reduction, and then you raise up the voltage to normal. You do the reduction, and you raise up. You do this on and off, on and off. We call it on-off. And you do this test, you will measure the power. You measure power. So one thing you claim is that you claim that the difference between these two power curves is a reduction due to your voltage reduction. Is that true? That's certainly not true. The reason is because you're talking about 1 or 2%, energy difference, energy consumption difference, and the load are always changing. We know that. It's always changing time from time. So the nature difference between the two time period in terms of load, the nature difference may already cover up your 1 or 2%. energy saving due to CVR. So that's not a very smart method, but industry using that because it's simple. And another method is a regression-based method. This is more commonly used by industry because it's easy to understand, easy to implement. If you look at the flow chart, it looks complicated, but actually it's super simple. I can tell you what they are doing is a kind of load forecasting. So the challenge is that I don't know what if happen. What would happen if I didn't reduce the voltage, right? So I just estimate. That's a very straightforward idea. So you model the load as a function of temperature and also a function of CVR on-off status. You do a linear regression model, and then you try to estimate, okay, under this temperature, what if CVR is not on? And then you basically reconstruct that load profile without voltage reduction using this simple linear regression. What's the problem with that? Firstly, linear regression, very low accuracy, right? So secondly, it's interesting when industry doing this, their regression parameters never change, okay? They do the training for the whole year. That's not true, right? Of course, we know these parameters should change according to different seasons or different methods or different time. So that's not an ideal method either, but you can see the basic idea between these two industry widely used methods. Basic idea is super simple. They're just trying to guess what would happen if there's no CVR, what would happen? So the real challenge is that I don't know what would happen. So they're trying to reconstruct that load profile without voltage reduction. That's all what they are doing. Okay, so there's a third method. Actually, this method coming from my PhD dissertation, the original ideas. I improved that over the past few years using different algorithm. We call it a load modeling based method. So it coming from the nature of CVR, thinking this way, why it works. When you reduce the voltage, the load reduced. What's the reason behind that? Because load is sensitive to voltage, right? So if you have constant power load, suppose the extreme case, all your load are constant power. If you reduce the voltage, what would happen? You increase the consumption. Why? Because current increase, your land loss increase. So you didn't reduce anything, you increase. You have negative CVR effect. Thinking in the other way, if you have a pure resistive load, all resistive heating load, if you reduce the voltage, what would happen? You have your maximum consumption reduction. So that's the nature of CVR, right? Load is sensitive to voltage. But in practice, the truth is that there's no pure constant power or pure resistive load. It's a combination of constant power, constant current, and the constant impedance load. It's a combination. And this combination we call it ZIP load. Some of you may have heard about that. It's a steady state load, has been there for decades. Industry use that. So the question is that how much is constant power, how much is constant current, and how much is constant impedance? So that how much decides the performance of your voltage reduction, right? So we call this a load modeling method. So what we are trying to do is to find that how much is a constant power, how much is a constant impedance, how much is constant current from the data, from the measurements. So basically you are trying to identify the parameters of these ZIP load models. It's a super simple model. You have, this is a constant constant impedance part, square to the square root of square of the voltage, right? So it's a constant impedance part, and you have constant current part, you have constant power part. And the constant power part also cover any non-voltage sensitive load. So they're not related to voltage. The change is nothing to do with voltage due to some other reasons. So all rounded to the constant power part. So the next question is that if I can identify this alpha, beta, gamma, I can calculate CVR factor. Later on, I'll show an equation that the function of alpha, beta, gamma, you can calculate CVR factor. Okay. So this alpha, beta, gamma, is that difficult to identify? It's not that difficult. The problem is that they're changing with time. Okay. Why they're changing with time? Because you keep switching on, switching off some devices that I don't know, right? So we see the aggregate effect, okay, at the failure high level. We're not talking about any particular house or any particular device. I'm talking about aggregate effect at the failure high level. Okay, when you turn off this light, when you turn on that light, and then you change the composition of this. So it's a time varying identification. So to do this identification, it's very easy. You formulate this optimization problem. Basically, you want your model output to track your measured power. This PI is measured power, and this VI is measured voltage. You want to identify alpha, beta, gamma. You see the index I because they're changing with the time. So it's changing with the measurement point. And you do this, you solve this optimization problem. It's actually, this can be solved by various methods like the least square type method because it's simple quadratic optimization. So this objective function is convex with respect to all the coefficients. So if you do not consider the constraints, you just do the first order gradient, you can get the optimum. Suppose you do not consider the constraints, okay? And then you form this equation, right? Then you write it in a matrix form. You can see that this is just written that derivative in a matrix form. So now one thing you can observe is that you need at least 3 measurements to identify the alpha, beta, gamma. So that's why you need to have this sliding window method. So the window size is at least 3. Okay, at least. Well, it's a necessary condition. It's not a sufficient condition. So if it's 3, does not mean you can always identify that, but at least you need 3. So why? Because if between 2 measurement points the change is too small, still can't get singular anyway. So you need to expand that a little bit to 4 or 5 measurements. So you can see that by using the sliding window method, I can identify alpha, beta, gamma for each time window. Okay. By default, is 3 measurements per window. But could be larger than that. So depending on how fast you sample the grid, for example, your measurement resolution, let's say, is 1 minute. Then that means this time window is 3 minutes long. Okay, there is an assumption under this. You assume the parameter didn't change within that 3 minutes. Assume they're constant. Is that true? Well, for steady state analysis, that's okay. That's fine because the load doesn't change that fast. And we're talking about energy saving. We're not talking about any dynamics or instantaneous power. So that assumption is valid. It's okay. It didn't change too much. Okay. But what about the constraint? Well, one thing we found that if you put the constraint into the optimization, it will cause the instability of the parameters identified. Using the real data, you will observe that. So one thing we have done is that we use this soft constraint method. Basically, you can see that the first part, all this sigma is still the first order derivative gradient, and the last 3 rows is trying to do what? Forget about this complicated equation. Thinking this way, we're trying to drive this identified parameter to this equation, and beta to this equation, and gamma to this equation. So what's that equation? So that equation gives you, the solution to the optimization problem, the previous optimization problem, and your previously identified parameter. So that when we do that, you change the epsilon 1, epsilon 2, you can change the weight. So basically, it's a kind of forgetting factor. So you're trying to make sure that your newly identified result didn't jump too much away from your previous identified result that reduced, I would say, the oscillation. A big jump of the parameters. So that's one way to do that. We call this soft constraint. Okay, it's not hardly constraint. It's just a soft constraint. You're trying to move towards this trend, but it's not hardly constraint. Okay, so suppose this work. Suppose all this work. You will have alpha, beta, gamma for each time window. Okay, for each time window, you will have that. And then what's next step? remember, CVR factor is defined as delta E divided by delta V. How about delta V? How about delta V? Delta V is easy. Okay, delta V is easy because it's a steady state analysis. We just use the voltage before and after the voltage reduction. Average them, assume it's almost steady, and do the difference. You will find the delta V. This is an approximation. I understand that, but it doesn't change too much because the voltage didn't fluctuate too much in this steady state distribution system, so it's okay. And then we need to calculate CVR factor, delta V, we know how to do that, delta E. And after some derivations, we'll find this equation. If you look at this equation, it has delta V, it has V, it has alpha, it has beta, it has gamma. So delta V, we calculate that. V come from the measurements, alpha, beta, gamma come from the identification. So you can calculate this CVR factor. And what's the problem now? It looks to me that looks to us that we address this CVR factor calculation. So what's the next thing? The next thing is that what we will get is a CVR factor with the index I. So that means for each time window, you have a CVR factor. Suppose each measurement resolution is 1 minute. That's for every 3 minutes you'll have a CVR factor. You can imagine how many CVR factor you have for a whole day and for the whole year, right? So is that useful to utilities? No, that's not useful to utilities. Utilities cannot report this to the regulation agencies. They want to report one number. Tell me, what's the CVR factor for this feeder? One number. Okay, so how can we convert this to be one number? Easy way, you average, so that doesn't work, okay? That doesn't work. So another way is that you can reconstruct the load profile, right? That's also something we can do. Suppose your CVR factor is correct. You already identified that. Times delta V, use 1 minus that, and this P-on is something you have measured. And use that divided by this load change. You get what would happen if there's no CVR, right? And then you can get the energy baseline that basically just using this plus some CVR off date. Then you reconstruct this energy consumption line, okay? And then you can easily basically you reconstruct this red dotted line, and then you can calculate the difference between the dotted line and the blue line, and you get the green area, and then you can calculate energy saving, just ESIC divided by CVR estimate of. Okay, this gives you one CVR factor for any length you want. You can do that for 1 day, you can do that for 1 month, you can do that for 1 year. It's up to you. But the CVR factor we have identified previously coming directly from the algorithm is actually, we call it time varying. Okay, time varying depending on how large your time window is. Okay, but to make it more easily understandable by the utilities and easily to be reported to the regulation agencies, we reconstruct the load profile and give you just one number for the CVR factor. Okay, so that basically finish the technical steps, how we get the CVR factor. One thing, just to give you a recap, so what data we have at the feeder head, I'm not talking about any household level, any distribution transformer level. I'm talking about feeder head because that's what utility is interested in, right? I report CVR factor for each feeder, not for each household. All right. So at the feeder head, you have SCADA measurements. Basically, I need your P and I need your V that come in directly from your SCADA system at different resolutions. Then you can use this simple load modeling method. We call sliding window time varying load modeling method to identify the parameters of the IP load model, and using that parameters to calculate CVR factor. Of course, eventually you want to report only one, so you somehow aggregate them together to be just one number report to the regulation agency. So that finished the whole process. So let's do some testing. So this, there are two data sets, D2 and D3, coming from ComEd. Real data, okay? The figure you have seen is real data. And they have done that in 2016. Well, they have done that every day, actually. So this data is just 2016. And one data set, this data set actually have 5 resolutions, 5 minutes up to hour. And both data sets have CVR on and off tests. In D2, so CVR is applied during this time frame and the other time frame. So one thing you can see that in D2, you apply CVR continuously. You didn't do that, on off every day. You do that for a long time, multiple days, and then you raise the voltage back. And then you lower down the voltage, you do that for multiple days. You stay at the low voltage for multiple days. But D3 is different. D3 is more like an on-off test every other day. So today is CVR on, next day CVR off. Next day CVR on, next day CVR off. So it's a 2 different way of running CVR. Okay, verification setup, we actually, sorry, I said 3 cases. I removed one because of the time. So let's talk about these 2 cases. One is the base case. It's clean data, okay, clean data. And we use this 30 minutes intervals. Second one is at 30 minutes interval with different randomly selected missing data. We want to just see what's the data quality's impact on your evaluation result. Okay, so here are the results. So for different methods, comparison method, regression method, load modeling method for different data cases, D2 and D3, you can see the CVR factor. Let's focus on the CVR factor side. So one thing you can observe is that for D3, it's okay. It's not very, I would say, it's not very diverse. So you have this one method give you around 1% CVR factor, and the other method 0.8, and the other method 0.8. So that tells you actually there are some confidence in terms of results using different methods. But D2, it's everywhere. It's interesting. It's everywhere. So for comparison method, it even shows you the negative effect. And for the regression method, it shows you just some unreasonably large CVR factor. 3 is too large. From experience, we know it's too large. And from experience, we know that CVR factor is not active for this feeder because it's not a randomly selected feeder. It's actually a specifically selected feeder. It will produce some CVR effect. So the low modeling method is more stable, give you a relatively reasonable CVR factor around 0.8 within our normal range. So that's case A. So case B is showing you at different missing data level, what's different methods, impact on different methods. Again, you can see that load modeling method, because of its identification algorithm, actually is pretty robust. And the regression method is okay. It also shows some kind of consistency, but this comparison method is too rough because the method itself is too rough. It just gives you everywhere, just results everywhere. It's not trustworthy at all. One thing you probably want to ask is that which one is true? Which one is true? So the answer is that I don't know, because you will never be able to know what would happen if I didn't do this. So there's no ground truth. In terms of real data, there's no ground truth. Because you reduce voltage, you cannot do anything else. Okay, so I will never know what would happen if I didn't reduce the voltage. So that's a real data. That's a real data. And if you really want to create a ground truth, I did some simulations for Comet using their real feeder. So under simulation setup, I don't have time to go through the details. If we have time during the Q&A, I can show you the results in the backup slides. So if we do simulation, I have full control of the load. So that means I can reduce the voltage. Of course, this load is also changing. I made it changing with time using the real data. The only assumption I have to make is the load model. I have to make the assumption. And then I reduce the voltage. Then I can bring back the voltage, run it at the same condition, load composition. And then I can easily find the difference between the two. That's the true CVR factor. That's not true CVR factor for the practice, okay? For the field, that's not true because you still rely on your load model assumption. But that's true under this simulation setup. And one thing I can tell you that this load modeling method can give you the true CV factor. I can show results if you have time. So, in this way, through this way, at least give you some kind of confidence. Okay, this may work. This may work. But in practice, I cannot verify because there's no ground truth. So that's the tricky part of this work. Again, everything you have seen will show up in the IEEE standard P3102 later this month. Can share with you after standard come online, or you can go to IEEE Explore, you can find that. I would say maybe second half of this year, you will find that online. Okay. So the other piece of work I want to talk about is more about smart meter data analytics. I want to provide you a background of this work. I told you that actually the work itself, I'm trying to use smart meter data to estimate the secondary distribution system voltage. You may be wondering why you want to estimate that, because it's measured by smart meter. Why you want to estimate that? So I want to estimate for planning purpose, for what if scenarios. So this is actually under a bigger project called the MOCAP project. It's funded by DOE through Sandia National Lab. So they're doing solar hosting capacity analysis. So that means, okay, for a household, do you approve it to install a rooftop solar or not approve? Okay, so that's what we call the solar hosting capacity analysis. So what's the constraint for solar hosting capacity? Two constraints. One is the voltage. You don't want the voltage violate the standard range. Okay, one is voltage. The other constraint we call thermal. If you push back solar, if you have very large solar, you push back solar through the distribution transformer to the system, it should not overload the transformer. Okay, so two constraints. So today I'm talking about the first constraint, not the thermal one. Okay, the voltage constraint. So to calculate the voltage constraint, one thing you can do, you can run time series power flow simulation, but that takes forever. Takes a long time and relies on the accuracy of your system model. Another way you do this model free, you identify the, we call it voltage to nodal injection sensitivity. If you identify this sensitivity, you can answer a question, what if I have this injection? What if I have that injection? Will that violate this? Will that violate that? Okay, so that allows you to estimate the voltage range without running power flow. So that's the basic motivation behind this work. And of course, there are some voltage issues. We know that at the secondary distribution level, if you have a high penetration of DERs, like shown in this figure, it's a real figure, okay, real data. It's not synthetic data. So model-free voltage calculation is what I have explained to you. It's very promising. It's not a new topic, by the way. So some people have already done that. Actually, many people have already done that. But the problem with that is that, firstly, usually they overlook, neglect the secondary distribution network. Should not call it network, because secondary distribution usually some drop lines. At least you neglect some drop lines, okay? At the secondary side, you assume that all the customers directly connected to the primary side. That's not true, okay? There are some drop lines on that. And also, you need to think about some extreme cases. When you have extreme solar penetration or extreme solar generation, or what's the voltage? So that part is something that the existing method didn't consider. So what we have proposed is we call it some kind of physics-inspired neural network. This is also a very hot topic, physics-inspired, physics-informed, many different names, using the smart meter data to do that. So how we do that, why we call it physics inspired. So look at, this is a simple feeder example. This part is primary feeder. Primary feeder means or primary lateral, whatever. So it could be three phase, could be single phase. And let's say maybe it's 13 kV, okay? And then through a distribution transformer, where's the distribution transformer? I think I draw it here, distribution transformer. The distribution transformer lower down the voltage to 120, 240 volts to your house, okay? And supplying multiple houses under this distribution transformer. And your house is connected to this distribution transformer through some drop lines, not very long drop lines, okay? So we call this part secondary system or secondary network. We call the previous part primary network or primary system. Okay, so we call it physics inspired because you need to code. Somehow code this power flow equation into your neural network. It's a linearized diesel flow equation. Many of you are familiar with that, maybe, if you're working on distribution system. And in this part, you can see the voltage is related with power injection. Also related with what? Related with voltage at the primary side of this distribution transformer, right? That's a primary voltage. It's related with that as well. It's also has some kind of linearization error. Of course, you do linearize, there's a linearization error. So basically, this equation tells you three parts. The original equation only have this part, okay? The other two parts we add that. So basically tell you the voltage is related with the power injection, nodal injection. It's related with the primary side voltage of the distribution transformer. It's also related with some kind of linearization error. Okay, so now I believe many of you already guessed what I'm going to do next. Next is to learn each part through the smart meter data, through the real data. Okay, so basically you use a neural network to model each part, and you use the historical smart meter data to just train the neural network and learn each part. Okay, learn each part, and then you combine them together. You will have a estimation of the voltage. So that's how it works. Basically, three parts. And we call this physics-inspired neural network because inspired by this physics. What's the physics? Power flow is physics. Also, there's primary, secondary connections through the distribution transformer. This is physics, right? So then all of this through the data. And I'll skip the details because the learning process, the training process, and the testing process are pretty standard. There's no, very strange algorithm we use to do that. But the design of this is more about the design of this framework. This physics-inspired neural network is what we have done. And then we go to the case studies. We test it actually on multiple models. Some are real models, some are just public available a priori testing circuit. Some of you may be familiar with this a priori 12 bus and a priori circuit 5. That's a larger circuit. And also real utility feeder. We call it real 40 bus feeder. That's coming from LY utility. And we test different scenarios. Basic scenario without any solar penetration. And when we do the training, most likely we do not have any solar, okay, except for one scenario we want to try. And this is testing. And for different penetration level, we test different scenarios. One thing you observe is that actually for, let's say, maybe for scenario 4 or scenario 5, you can see that actually we push the solar penetration to a very high level. We call it extreme test case. This is to test, we call it extrapolation, okay? If the system didn't see this before, this training before, can it extend its experience to new data set? That's we call it extrapolation, okay? Here are some results for different circuit, a priori 12 bus, real 40 bus, a priori circuit 5. And this is the mean average absolute error, I think, for different cases under different scenarios. It's not surprising that actually scenario 4 and scenario 5 will see a higher error because, it's just trying to test the extrapolation. You won't see these extreme cases in your training data, right? So this is very extreme cases. So you will see a slightly larger error, but still within the within the acceptable range. And you can see different method. One is PNN, that's physics informed neural network. That's our method. And DNN means just a neural network without any physics. And this linear neural network means you do not consider the primary side multivariate, so do not consider linearization error. Just that's just a simpler version. And you can, of course, you can see that without physics-informed information, you're expecting to see larger errors for any cases, especially for some extreme cases. That shows a very bad extrapolation capability. With this physics-informed neural network, it has a better extrapolation capability. That's not surprising to us, consistent with our expectation. Okay, again, so why we do this? I'm not using this to estimate the voltage. That's not the case, okay? I want to remind you the reason we do this is actually we want to just tell you what if I have certain solar injection, what's the voltage? Will that violate the range or not violate the range? So that's a major purpose. So I didn't show that result. That's a hosting capacity result. So I only show you the voltage sensitivity result here in this part. Okay. So I think we're running out of time. I want to conclude my presentation. Just we talk about CVR, and actually the real challenge for CVR assessment is it's hard to distinguish the impact from voltage to other impact factors. So that's a true challenge. So we're trying to use various methods to correct that challenge. And so for utility companies right now, they're still relying mostly on the regression method. ComEd is slowly adopting my method and load modeling method, but slowly adopting that because their concern is that if I use a new method producing different results, how can I report to the regulation agency? So, but they're slowly adopting that, and the AES is also in part with me just using this load modeling method to analyze their CVR effect as well. Also, we show you using smart meter data and physics-inspired neural network to guess the secondary voltage, basically testing the extrapolation capability and the different scenarios. So future work on this physics-informed part will be to see how it's adapted to different topology change, voltage regulator operation, capacitor bank operation, this kind of thing. Okay, so I want to talk about future research a little bit. So I'll do this very quickly. Again, in the future, I will still focus on the distribution system research with techniques, big data techniques, machine learning, optimization, those are techniques. And applications or problems we're gonna to do still on the smart sensing, smart meter, micro PMU analysis, data-driven control, asset management. We're also doing optimization of DER and microgrids, and we're also doing continue doing the CVR assessment and CVR implementation in the future. So those are some, just give you an idea what would happen in the near future, okay? And also about the teaching, so what I have taught at our state, I listed all the courses. Some are new courses, basically on distribution system, protection, reliability, and some are old courses, existing courses on distribution system, power system in general, and the energy system in general. So I checked online and found a few courses that I think I'm comfortable in teaching for the Washington State University. I list them here as well. So I'm flexible, but those courses I found online, I read the syllabus, I feel I'm okay and comfortable in teaching them. Okay, so I think that's all for my presentation. Welcome to any questions.
First, we will go and see if there are questions from online participants. You can mute yourself and ask a question. Yeah, we have 12 online.
Oh, yeah, I can't see it. I can't say it is shared screen.
Hey, thanks, Manny. This is Jeff Daigle from P&L. And I have a question about, are you seeing trends in CVR based on the changing composition of the load?
Yes, we do see that. So because there are more power electronics based load, so it tend to be more constant power type load. So I think when ComEd and AES and other utilities in Iowa, when they do that, they mainly focus on the residential feeders. Okay, there's no commercial, no industrial for sure, because those loads are more constant power type. You will see much less even negative effect. The future trend is that with more lighting system are changing and heating system are changing, power electronic based load more and more, you will see less and less serial effects. That's a future trend. But still there, it's not zero. And considering the easy implementation and almost zero cost to do that, so utility are still very interested in doing that, become a standard procedure for many utilities in doing that. And many of them are also very interested in doing that for emergency, just reduce the peak power. I do not run that for energy saving, but I reduce the peak power during the peak day. So that's a lot of utilities are also interested. Recently, we have seen some research, not the demonstration, not the utility run research. It's a research by some university groups. They're claiming that by reducing voltage, you will have higher efficiency of the motors and higher efficiency of some power electronic components. So that part I haven't investigated too much, but that's their claim in the papers. So we'll see later. Thank you, Jeff, for your question.
Yeah. Other questions from online?
Yeah. Are you guys getting an echo?
No, please go ahead, Noel. We hear you well.
No. There was an echo earlier. I think Evan Edwards has a question.
Yeah, hi guys. Can you hear me?
Yeah, please go ahead.
So along these lines, we're actually in the final stages of prepping like 3 substation feeders for this application. And what we found was that, yeah, from an efficiency standpoint, Bonneville Power Administration is offering, conservation credits to utilities for implementing this sort of thing. The difficulty that we had is the AMI information that we do have, it's so vast and so cumbersome to sift through to get to the point where it's usable. One of the and I'm sure that the professor can attest that it's a big lift, especially for a small, medium-sized utility like ours. But we've actually gotten to the point where we're doing our last little bit of feeder preparation with modified capacitor controls and things like that. We're in the final steps of getting that stuff put out to do what the BPA considers an M&V period, where you run it while it's off and then run it while it's on. And we're pretty fortunate in our SCADA system is 5-minute interval data all the way across the board. So more to come on this. I think that this is going to be one of those the low hanging fruit from a conservation perspective is gone, and this is definitely one of those things to be paying attention to going forward, because this is like the next step.
Yeah. Well, thank you for your comment. I think for this measure, we don't need smart meter data. We actually need SCADA data. Smart meter data will help to some extent, maybe calibrate some results. But most utilities, they're not interested in household level, customer level savings. They're more interested in feeder level savings. So SCADA data is good enough for our studies. Smart meter data may help us to build a more accurate household level load models that may help you to do some simulation studies.
Essentially that's what we did, was we wanted to make sure to kind of give us a range. How low could the voltage be reduced without causing an issue? So
that's a useful need of smart meter. So it's more about the implementation side. You actually create some kind of feedback loop, especially at the feeder end or some trouble areas. So you want to make sure the customer receiving the standard voltage range still. So that's true. Yeah.
Yep.
That's true.
Any other questions from online? Okay, thank you. Now we will go to questions here.
Yeah, I had a question about CVR. So it makes sense to me that you would exclude industry for things like constant power loads. But let's see, all the data was taken in Iowa at home level distribution?
No, actually the data we collect from multiple utilities, the data you have seen is from Chicago. from ComEd. It's not home level data, it's a SCADA data at the substation level. For different feeder, at the feeder head, there's SCADA data doing that.
Okay, so I guess the question was more of if the load profile were in a different place that say maybe had electric heating or a lot of AC, where the energy usage is based on total energy need rather than some kind of constant power.
The question is very valid because for the thermal, we call it a thermal controlled load. For this kind of load, suppose in this way, if you're using the water heater to boil water, it doesn't matter how you reduce the voltage, energy consumption is the same, right? So it just takes longer to boil the water. So in that part, there's no CVR effect. There's only power reduction effect. For pure power reduction, that works. But for energy saving, no. So that part is not for energy saving.
Right, and so what I mean is, can your model differentiate between those things, or would you, in the case of having a large portion of the load being energy dependent rather than power dependent, would you get inaccuracies with your model?
Well, here's the thing. The model itself is trying to identify low to voltage sensitivity. It does not distinguish whether it's it's a thermally controlled load or it's any other load, right? So if you ask me this question for each time window, no. So for each time window, you won't differentiate whether this is whether this saving is instantaneous. I mean, it's temporary saving, or it's a real energy saving. So for each time window, no. But along with the time window, yes. Because when you zoom out, when you have a longer time period, eventually all this effect will be considered into the low to voltage sensitivity. So for longer time period, that can capture somehow, but for each time window, no, it doesn't capture that. Yeah.
All right.
So, that's correct. Any other questions?
Yeah. So looking at the zip load, you said that the most of the loads that we have in like the residential areas are not really constant power loads, but at least it's not zero.
It's not zero.
We still have some. So
yes.
Now, when you apply CVR to a constant power load, obviously, like you said, you are kind of increasing the power
yes.
because the I2R loss is also increasing.
Yes.
So wouldn't that have like a counter effect on what you are trying to gain on the other type of
well, so that's a good question. That's why when utility implement CVR, they need to, it's not randomly selected feeders, okay? They need to do some pre-studies, okay? This feeder, I feel any feeder will have constant power.
Yeah, sure.
Right. So, but this feeder constant power is not dominating. So that's the point. It's not dominating. Okay. So that means, okay, the constant current and the constant impedance load is dominating. So even though the constant power load produce some counter effect, like you mentioned, the negative effect, but the other part provide the positive effect. If you look at the aggregate level, at the feeder head level, you will see that it's still positive, right? Okay. So does not mean there's no constant power load. It's always there anyway. Okay. Yeah. And if you go back to your question about that thermal control load, there actually the regression method I mentioned to you, why we model the load as temperature, is trying to actually capture that part, remove that part a little bit, but it just didn't do that in a correct way. Because if you really model this, it's complicated. It's complicated, very complicated process. So utility won't do that. So they just want some easy process. So that effect is not removed. In any method, it's not removed. Yeah.
Yeah, I have a question,
sure.
Jai. You know, some of the estimation work that we have worked on, what we have seen is for the estimation, you kind of the estimation sensitivity improves if you increase the sampling rate.
Yes.
And so I'm wondering if you have, say, smart meter data versus SCADA data versus, say, micro PMU data. Do you think the estimation of CVR will get better?
Theoretically, yes. But if you're thinking this way, man, so we're not talking about any dynamics. We're talking about the long-term effect. And so the changing of the load is not that fast, especially at the distribution side. So for this SCADA data, let's say our data set go 5 minutes. It's almost good enough to capture the steady state load change. But if you have micro PMU data, actually that's something I will study in the next step. If you do have micro PMU data, you will be able to identify this load in a much more granular way. You probably can see a lot of interesting jumps up and down using this data set.
No, what I'm thinking is if your data is overdetermined, you have a lot more redundancy. And so if you are trying to fit some kind of parameter to a model, then the more data you have, and maybe you have to process it some.
Yes.
We can chat offline, but I think the estimation may improve. If you have
the accuracy of that estimation, you have more data source. That's what you mean.
Yeah, you have more data points.
Okay, I misunderstood that. I thought you talked about sampling rate. So that you have smart meter providing information, you have SCADA providing information, you have micro PMU providing information, you have redundancy in terms of.
So you introduce more redundancy.
Theoretically it does improve. Of course, it will improve.
Yeah, that was one question, and then second one, again going back to Jeff's question about changing loads. What do you think will be the impact of EV, the charges on CVR?
That's an interesting question. If you reduce the voltage to an EV charger, of course it has to charge the same amount of energy anyway. But I don't know how it affects the charging efficiency. So that's the question. So basically, you're not reducing the energy, you're reducing the losses. I don't know if it reduces, but whether you can reduce the losses. Even if you can, that should be minimum, minimum effect.
Okay, thank you.
Okay, thank you.
Other questions? Yep, go ahead.
Thank you for the nice presentation, Dr. Wang. I just wanted to, wanted to clarify if I understand your load modeling based method correctly. So as I understood, first you, based on some test data, you take its data and you estimate the zip model first, the parameters of the zip model. And then you use those parameters and you model the whole optimization problem in an analytical manner and then solve for the CVR. Is that so?
That's not the case. So everything is performed, you can think it's an online manner. So when you have data coming from here, you have a sliding window, just scan the data, and in each window, you'll give you a result. It's not a training process. You don't need the training. It's just 3 equations. You have 3 measurements. You can give you the unknowns. You can solve for unknowns. That's good enough.
So you mean you solve for the 3 parameters as well as CVR in one go?
Just one. Just a one-time window you have. It works super fast. It's super fast. Yeah.
Okay. Yeah, got it.
Yeah. Okay. Great. So there's no question about the neural network smart meter. People are now interested in that. Some people will be interested in that.
We have a few students who are working on that topic, so we will see. And the 2 experts in the room.
They laughed. I was expecting question from them. They laughed. It's okay.
How about online? Do we have any questions on the machine learning part of the?
Well, you don't have to ask. Okay, I'm just checking.
Our local expert who has questions on any topic is Professor Saeed.
Saeed may have question on my teaching. Interesting.
Okay. Thank you all.
Thank you all
very much.
Thank you for your time.
Thank you.
Thank you for coming.